let's talk about buffers. They're actually pretty amazing, and one of the reasons that you can drink lemonade and coffee and all kinds of different substances and yet not end up as a pile of bloody goo. Pretty amazing what your blood has in it that allows your pH of your blood to stay at a pretty constant level. In order to understand the content of this video and to make them accessible to yourself, you'll want to be very perhaps is a little strong, but you want to be knowledgeable about what conjugate acid-base pairs are and how to figure out, if you're given an acid, what its conjugate base is, and if you're given a base, what its conjugate acid is. And then how to figure out charges on ions and how they change if you add a positive or take away a positive. You'll also want to be aware of strong and weak acids and bases, and then generally knowledgeable about pH. So what is a buffer? Well, it's a solution which contains something which causes the solution. It's a solution that contains. It's a lot of solutions. Basically, it's a solution that resists the change in pH, and it contains a weak acid and a conjugate base, or a weak base and a conjugate acid. Looks like I have a typo in my slide. I kind of think of this as like ingredients. Or to a meal. We can talk about the ingredients to a dish, and we can talk about how the dish is really delicious, and that's kind of like, or how it tastes. It's spicy or it's sweet or whatever. That's this idea that the solution resists changes in pH. And we can also talk about the ingredients to the dish. So let's say we're making some kind of soup, and we have some vegetables in there, and we have some salt and some garlic. That's talking about the ingredients that make it up. So that's our weak acid and our conjugate base, or a weak base and a conjugate acid. I think about buffers as kind of like a piranha. And they, when you add acids to them or bases to them, the buffer eats them. To know what a weak acid is, you need to know what a strong acid is, and to know what a weak base is, you need to know what a strong base is, because everything that's not a strong acid and not a strong base would be weak. So I've listed here our 7 strong acids that you should be aware of and memorize for an exam, and our strong bases, which you have some help from the periodic table on the strong bases, because the alkaline metal hydroxides, so pretty much everything from lithium down to cesium in the first column of the periodic table, when those are paired with hydroxide, those are strong bases, and everything from calcium to barium, which I guess really just includes strontium, those are your heavy alkaline earth metal hydroxides, and they're also strong bases. So, are you a buffer? If we remember that the ingredients of a buffer are a weak acid and a conjugate base, or a weak base and a conjugate acid, then when we're looking at two substances, what we're looking for and what we have to ask ourselves is, do we have a weak acid or a weak base? So when I look at this first substance, I see that there's an H out front, and so I know that it's an acid. And this is an acid that contains the acetate ion. This is acetic acid. It's not one of our strong acids. So that tells me, I could have a buffer. I need to check, though, the second part of the buffer, because I need a source of the conjugate base of acetic acid. So HC2H3O2 is my acid. Acids lose hydrogens, and so its conjugate base would be, after it had lost that hydrogen, which would be C2H3O2 negative. Now remember that hydrogen out front is the only acidic hydrogen in this compound, and so it's a monoprotic acid, and it's just losing that one. Let's go back and look here at my substance. Do I have a source of acetate ion? Well, I do. And students are sometimes confused because initially, excuse me, they look at that potassium there and think that it's significant. Because, hey, you've been taking chemistry, and elements that are written as part of compounds are significant. But in a buffer, we don't have, if you're going to make a buffer, you don't have free acetate ion as something that you can just find on the table and put in solution. What you have to do is find an ionic compound that contains acetate and put it into solution, in which case then it will separate into its ions. So potassium acetate is basically a source of acetate ion. And we're ignoring the potassium because it's just there to sort of give acetate a helping hand into solution. So indeed, this is a buffer. It has a weak acid and the conjugate base of that weak acid. What about HNO3 and NaNO3? Well, HNO3, when we check our list of strong acids, shows up on that list. So this is not a buffer. HCN and KCl. HCN, we check our list of strong acids. It's not there, so it is a weak acid. So we're looking to see if we have HCN's conjugate base. So the loss of a proton, that hydrogen ion, should give us the conjugate, and that would be Cn minus. Well, we don't have Cn minus, we have KCl. So this is not a buffer. So this one was a no, and this one is a no. What about NH3 and NH4Cl? And the reason I'm talking about this one in a video is to make sure that you're aware of NH3, because NH3 is a weak base. It's the one non-hydroxide containing base that you want to be aware of. That's ammonia, NH3. And when we look at this, we see there's 3 hydrogens here, and then we have an N-containing compound with 4 hydrogens. So NH3, if it's a weak base, its conjugate acid would be after the base had picked up an H+, and so that would be NH4+, or the ammonium ion. We've got chlorine attached to it because, again, we don't have free ammonium ion just running around in the lab, and so we need an ionic compound that we can put into water to make this buffer. So yes, this would serve as a buffer. Next we have lithium hydroxide and water. And water is an amphiprotic or amphoteric substance, meaning it can either act as an acid or a base, so it's definitely not as strong either of those. And so we go over and check the lithium hydroxide and see that's an alkali metal paired with a hydroxide, and so that is a strong base, and this is not a buffer. Nope. When you have a buffer, that piranha that was gobbling up any acid or base that we were given, that's happening, that gobbling action is happening via a chemical reaction. And let's look at an example of what's occurring there, and let's consider acetic acid as our buffer. Well, buffers, as you know, have 2 parts, the weak acid and its conjugate base. So if I say I have acetic acid as a buffer, I really mean I have acetic acid and the acetate ion. Acetic acid was on the previous slide, so it's HC2H3O2, and its conjugate base is C2H3O2 minus, which, as you know, is the acetate ion. When we add HBr to this buffer, we want to address and identify what HBr is. Well, it's an acid, and acids, we know, don't generally react with other acids. They're going to react with bases. So in our buffer, we knew that this was the acid, the acetic acid, and the acetate ion was acting as our base. So HBr is an acid, and it will react with the base. And when it does that, we will produce, since we know this is our acid, and this is our base in this reaction, we'll know the acid loses the hydrogen, Bronsted-Lowry definition right there, and the base will pick up the hydrogen, and we'll have those 2 products. So notice, this is sort of the magic of buffers. We started with a strong acid, HBr is a strong acid, and we turned it into a weak acid, on top of which all of our buffers will be engaged in an equilibrium reaction. And in this case, I'll have H3O+. Where, if we think about Le Chatelier's principle, we just created more acetic acid. So we added more reactant on this end. Le Chatelier's principle says equilibrium will shift to make more products. So I added a strong acid, it turned into a weak acid, and then equilibrium consumed even more of that weak acid, and so overall, I don't see much change in my pH. Let's look at what happens when we add a base. In this case, I've got KOH, which is our base, and it's going to react with, well, it's going to react with acids. So it's going to react with acetic acid. For clarity's sake here, I'm going to ignore the potassium for the moment, just to sort of give you a clear picture of what's happening here in terms of my hydrogens being transferred. I can ignore the potassium in this case because it's what's called a spectator ion. It doesn't actually participate in our reaction. So my acid will lose a hydrogen, and my base will pick up a hydrogen, and that will make HOH, which we also know is water. And then it will also make acetate ion. So this is even more amazing. I started with a strong base with KOH, and I produced water, which is neutral. Pretty cool. Let's try this again. This time I have HNO2 as my buffer, part of my buffer. So the other part of that is the nitrite ion. And I'm going to add lithium hydroxide. Lithium hydroxide is a base, so it will react with the acid in my buffer, which is HNO2. And it will make, I'm going to ignore my lithium here for just a sec, it will make HOH and nitrite ion. I can also add HCl to my buffer. HCl is an acid. Acids lose hydrogens, so it will react with my base in the buffer, which is nitrite ion, and I will make HNO2 and Cl-.